Audio. Switch off your audio. Okay, so I will share the, where can I share it? Switch off your audio. Now, we have used several packages. Upfront, I have given description about each of these packages. The first one is Geopandas. The second one is Shapely, Matplotlib, MapClassify, H3 Pandas. Now, I have given links to each of these packages. For instance, you'd find Geopandas documentation if you click on this link, Introduction to Geopandas. If you click on this link, you would be able to see what Geopandas is. I haven't given you the IPyNB because that's a part of the submission. And also you have Shapely, Matplotlib, Map Classifier. So I'll explain what the task is. Initially, I have followed a mechanism in which we try a simple one first and then move on to the real application. So then you can actually build your solution on a very simple data set, on a sample, and then take it further to the task that you require to do. Now here, upfront, I put Geopandas, Pandas, H3 Pandas, Matplotlib, PyPlot, Shapely, Geometry, LibPysal, ISDA, Plot.ISDA. So ISDA is the exploratory spatial data analysis package in Python. And we would need ISDA to calculate the Moran's index. If you remember, we discussed about the local Moran index in your previous lecture series. And H3 Pandas is used to create the hexagonal structure, the grid of hexagons that you see in your visualizations. Why am I doing it? It's because it's easy to find correlation when we create these hexagonal structures, and also they are pretty much accurate in terms of the spatial association, because if we are using like normal square grids, then because of the angles, there is an issue where you how to get that angle measurement, whether they are adjacent or not. But when you are using hexagonal structure, that particular issue goes off. So that's why I'm creating hexagonal grids. Now to start with, we have a dictionary, Python dictionary, and in the dictionary, the name is data, and you have the tokens like latitude, longitude, rank, and the respective lists that are under this particular dictionary name titles. So the first task is to get this data, and if I run this, I have to initialize it. Let's wait until it is connected. So I'm going to import the respective packages. If you have not installed them, for instance, H3 Pandas is not here, then you have to install it from here. So I will install H3 Pandas. Pip install H3 Pandas, and then it will be installed, right? And now if I run it, I should be able to, I have to, anyway, we'll focus on libpysal will be needed later, but I think ISDA should be there, hopefully. Let's see. If ISDA is not there, I have to install ISDA again. Yeah. Anyway, ISDA will be coming later, so we'll just focus on the first part here. Now, initially, I have named a list called geometry and that is taken from point xy. Point comes from this. This is not a normal name. It's P with capital P. Point. Point comes from this thing, Shapely. So Shapely, remember, most of these packages are named in a way that you can remember them. So in Shapely, you would find point, polygon, and line string. Those are the point, lines, and polygons that we find in spatial analysis. So Shapely.geometry, any type of geometry found in Shapely, I have imported point and polygon. Remember, they are capital P and capital P in polygon. So I am using that point command under point xy, x and y. For xy, I'm going to put point geometry xy. For xy, in the zip data means now it is a dictionary, and I'm going through that. Zip data, longitudes and latitudes. You can see longitudes and latitudes. So longitudes here becomes x, latitudes become y. So I put that into a geometry file. Now I have created a point geometry file. So this is the conceptual methodology that you need to keep in mind. We are creating a point geometry with xy coordinates. The next thing is I am going to take this geometry, which is my point file, and the dictionary, which is my attribute table, right? I have a point geometry and data is my dictionary. Under EPSG 4326 is the coordinate reference system. So these are the three things you need when you want to create a geodata frame. You need data as in the attribute table and the geometry file, which is a point or a line or a polygon file. And I have created that using Shapely geometry. Okay. And I have given the coordinate reference system. Then GPD is the way that I have imported Geopandas, import Geopandas as GPD, and I'm applying the method geodata frame to create the data frame with the attributes and the geometry file. So my geodata frame, GDF, should contain the geometry and the data. If you remember the previous lecture, we talked about GPKG, geo packages. In geo packages, you can find multiple types of data in terms of points, lines, and polygons. But when we are referring to a geodata frame with just point geometry, you will find points only. Now I'm going to plot this using PLT, matplotlib. I'm going to create a graph file X where the geodata frame plot method figure size is given and the color also given for the points and the edge color is also given. These are like normal Python visualizations. And plot title, observation with labels, you can change them. But the important thing is I am referring to the GDF, geodata frame. When I run it, you would see observations with labels, like a usual Python visualization. Now, if you want to show extra things like the tag values or XY values, you need to use the usual Python visualization tactics. Now, if you look at the first part, it's basically the one that I have used in the previous case, creating the same visual. Then you have, what is this GDF iteros? You remember what iteros is? Now, if you have worked with pandas, iteros means going through iteration by rows. So you take a data frame and go through the rows. So you, in order to go through rows, you need IDX, that is the identity or the ID of that X value, and the row number. So you go through the rows, gdf.iteros, and then I'm going to annotate the plot using different commands. Now the text in the plot, PLT, becomes the string that is found in the rank of the data frame, row rank. So you go to the row and the rank there. So rank coming from the column name and row ID come from the row that you are in. So the rank will be like going through the rows, right? Then you have XY. XY is the X and Y coordinates. They come from row geometry dot X. The row will be that row value, and there's a geometry column, the X value in that geometry column. That's what it says, comma, row value, geometry, of X. Row means not row, R-A-W, this R-row, row. The row is the record dot geometry, that Y value there. And then XY text 3, 3, that's actually to make sure that it's a bit further away from the label, the dot. And then you have text coordinates, offset points there, and font size 9, color dark red, depends on how you want to show it. Then usual plot command, X label and Y label. Then you have the show. If you run this one, you can see that the longitudes and latitudes are there in the axis values, and then you get the plot observation with labels, right? So basically, why we are using a simple data set like this dictionary is to make sure that we are following the method and we don't get a lot of issues. If it is a large data set, there can be many issues if we don't run the code properly. The next one is an important task because we need to know what is the geodata frame coordinate reference system. Now, in the first case, when I create the geodata frame, when I imported the geometry, I use the coordinate reference system as EPSG. I use the coordinate reference system as EPSG 4326. So when I use EPSG 4326, I initialize the coordinate system to be that, right? So if you don't know about your coordinate reference system, for instance, if you are loading directly a shapefile to your workflow, you need to check the original coordinate reference system. That is because if you are not familiar or if you are trying to do an analysis, I will show you why that is. So in this case, I have given EPSG 4326 to make sure that I am in this coordinate reference system. It's geographic coordinate system. And when I check the original CRS, I get 4326. That is the original coordinate reference system that I have used. All right. Now, there are several options that I have used. These are actually to make sure that you understand the concept. So what is a buffer? A buffer, as I've explained in your previous lecture series, buffer is when you have X such that X is within a given contained distance from a given point. Mostly, if it is the same distance, that will be a circle, right? A buffer is like that. To have a buffer, you need to have, depending on your conditions, a starting point. So I have created a custom point where the point geometry is in the coordinate -88, 42. So -88, 42, if you look at your chart, your graph, observation with label, you can see -88 would be somewhere further to the right and 42 would be there at the bottom. So I have created a point called -88, 42. If I run this, you would get a custom point. Then you have buffer distance. This is the part where the coordinate reference system is important. Now, remember, we have different types of coordinate reference systems. When it comes to the points like geographic coordinate systems, you have degrees, minutes, and seconds. But when we are doing the buffering, we are using a distance, a point distance in the Cartesian plane, or what we call Euclidean distance. So in the case of buffer distance, when I put 0.001, if the custom point is developed in a geographic coordinate system, then the buffer value would be applied as a degree value, right? So the distance will be applied as a degree value. Now I have given buffer geometry custom point dot buffer. I'm asking it to buffer. When I create the custom point, I use Shapely point geometry. Because of that, it has a method called buffer. That's why custom point dot buffer works. Okay. So custom point dot buffer method, buffer distance is the distance that I have given. This is 0.001. As I said, if it is a degree, that is the coordinate system is based on degrees, it will be degrees. If it is projected, then it will be in meters, right? So when I run this, with the coordinate reference system being applied as GDF.CRS, which is geographic coordinate system, you would get a buffer GDF of this nature. So what has happened here? I have created a point using the point method and then buffer I have applied a buffer of a distance. So you have a point and I have created a buffer around that point. Okay. And then I have created that buffer into a geometry, and then I have created geodata frame. GPDs, Geopandas. I have created the geodata frame using the geometry, buffer geometry. You can call it a geometry because I have applied Shapely point, right? Custom point is coming from Shapely. It's a geometry. Put the geometry as the buffer geometry, and coordinate reference system is geodata frame coordinate reference system, which is the initial one that we use. Now look at what happens. First, I will run this. Now, what do you think about the buffer? Is it a circle? Is it a circle? It looks like an egg shape, right? So that is because we are using geographic coordinate systems here. It's applying 0.01 as the degree for the buffer, 0.001 degree for the buffer. And when I run this, all the other codes are the same, iteros and everything is the same. But this is the case where I have applied the spatial part of it, where I have asked to overlay the buffer by plotting its boundary. So the buffer is spatial. Don't forget that buffer is spatial because we create a point geometry. So when I use buffer GDF, that is the distance from that point, 0.001 degrees. And I'm asking to put the boundary of it just as the boundary, not the colored fill on the map. So it belongs to -88, 42. That is where that center is. Remember the point was created there. And the buffer is that circle with the black color. Okay. So it looks like an egg shape because still the buffer coordinate system and the point coordinate system, they both belong to geographic coordinate reference systems, right? So if you are doing an analysis, particularly related to business context, if you are looking at a local context, most often you would have to project your coordinate system. So that is what we call projected coordinate system, UTM, Universal Transverse Mercator Projection, where we convert the coordinates into distances. Degree, minutes, seconds into distance. We project it. So I have given you a different condition, select a point based on your condition. So you can follow that, but I will show you the most important thing. Now you can see when I apply here, I have selected a point inside my observation points, but instead of degrees, I have applied the distance, buffer distance now is in meters, because the projected coordinate system references are used. So I have just given the point and I have applied the coordinate reference system as the GDF projected coordinate reference system. So the distances now applied in meters when you go to the buffer, right? So I think you can, once you read the code, now you will be able to understand it. I'll not take your time on this. And the next one is a hex bin projection, or rather hex bin visualization, where you have the visualization, and I have created a hex bin using PLT, plot command. And what you see here is a simple visualization where you have these honeycomb-like structures. And if the points are inside this, then the number of points will be colored based on the density. So you have 2 points in this top part. So because of that, you have a yellow color, and then you have green color, and then purple all around. So because the points are such that. But the problem is these hexagonal structures are only available, hex bin is only available in PLT. It's a visualization command. But if you want to do spatial analysis, you have to put the grid as a spatial grid. To do that, we need H3 pandas. So that's why we need H3 pandas. From H3 pandas, you can create this hexagonal grid. H3 pandas is developed by Uber. So Uber holds the right to H3 pandas. They have this grid structure. So what I have done is I have applied this hexagonal grid on that. And you can also go further and improve the resolution, because I want to count the number of points inside the grid. So these can be tourist attraction, like the same data set that you are using for your project. That's what I have used here, right? And then what I did was I tried to count the points, increasing the resolution of the hexagonal grid. As you can see, when I increase the resolution, you can see points become isolated in the grids, but 2 points remain inside, and you can refer to the spatial resolution. And then I create a Moran index. Look at what Moran's index is in your previous lecture series. I create a Moran's index to find local clustering, whether there is a correlation between the points, right? All these codes are like easy to follow because PS is Faisal, weighs directly from Queen's contiguity from the data frame, and you get the hex grid data frame which was created by H3 pandas. And that's what the code is about. So that is basically trying to understand whether there is a spatial correlation between the points, right? That's the starting point. Like you try to get your data and get familiarized with what to do. Next part is the real data set. So in the real data set, I have used the tactic that I used in the previous case as well, creating the drive folder, copying the drive folder to where you are doing your study, and then this Twitter data thing is coming from your project one data set, the data set that everybody has by now. And the same analysis, right? Same analysis, the codes can be slightly different in some cases, but I want to explain to you about this convex hull operation. Convex hull, I think I explained, is about like a rubber band going through the points. So everything is like squeezed in that convex hull. What I have done is I have used, if you use your Twitter dataset, you would see how many data points are there. Then I use that and I union them all. GDF.union all means assume the point set as a complete entity, single entity, and I create a convex hull around it. So all the points will be created around. So if you want to have a subset of this, you can create a slicing command, take a part of it and make it union, and then create the convex hull. It depends on your analysis. All right. Here I have created all the things and then created convex hull around it. Then I applied the same thing, right? The convex hull is a geometry. So I can apply the geometry command buffer distance 0.01. I have done this because if you tried this, you would realize because the points are located in a sporadic manner, sometimes the entire hexagonal structure will not be created inside that boundary. Like points will be outside of the hexagonal set. That's why I created a buffer, so that whatever the hexagonal structure created will be covering the point set. Okay. So poly GDF is, then forget about the names and look at the methods that I have been applying throughout. GPD data frame, geo data frame, and then you have the geometry expanded. Have the same command. And it's using H3 here, the poly sample, and you get the hexagonal grid. Then I use the same command I use with the small data set to cover the local Moran I scatter plot. Forget about data clustering and visualization. If you want to follow, you can follow that as well. I don't mind including them in your report. In fact, that would be nice. But at least up to this point, cover them in your Jupyter notebook and upload that as your first submission. Then there is a second submission about the report. So I will share this video with you so that you can listen to what I said and how to follow it, and then write a methodology, objective, and the results you find in your analysis, right? So what I have explained. So why are we doing this? In the real world, you would find similar issues. For example, nowadays they are looking at these wild animals, or looking at tourist destinations, or crime analysis, or any observation analysis, patterns. So this is how we do the analysis. You need to first of all create some idea about what you are going to do and then refine on it. This is basically how we do a spatial analytics project. Any questions? Okay, so I will share the video and I will give some time for you to do it. Please upload the notebook within today itself. The notebook, even if it is a half done notebook, that's fine. But at least do something up until taking the data from your data set. But the report needs to be done next week. Next week means you have 1 week. Do it and upload.